Okay, so welcome everyone to lecture 4 of the Advanced Intro to Machine Learning class. So conceptual 1 assignment is available, and I don't know if there's any other logistics. Do we have, are we clear on the office hours and quiz section hours? Is that clear? I think it's on Friday, Saturday. It's like a couple of them on Friday, Saturday. So okay. If you have any questions on logistics, feel free to let me know. So today's class, we'll do a recap of overfitting and regularization. Look at the famous gradient descent algorithm and stochastic gradient descent. And we'll look into the mechanics of it. It's kind of like the, you can say it's the algorithmic foundation of machine learning. Foundation. So it's not the only, like you still have many algorithms in machine learning, but kind of the foundation is based on gradient descent. And I think if we have time, we'll also look into classification problems in machine learning. Okay, great. So we start off with an in-class exercise. So remember we spoke about, we have like train error and then validation error. So the figure to keep in mind is something that looks like this: train, and then validation. And this is your loss function. Okay, so keeping this figure in mind, take a look at this question where you've trained two different models, A and B, and associated with both the models, you have these two curves, right? So, and then you have train error for A and train error for B, and validation error for A and validation error for B. So the question is, when model A is underfitting as compared to model B, or model B is overfitting as compared to model A, which of these hold true? Okay, so we can answer this on the polls, and the poll should be active. So just take a look at the poll and answer it there. So hopefully you had a chance to think about this question. So clearly, if model A is underfitting as compared to model B, the training error for A must be less than the training error for B. Would you agree? Like something that's overfitting will always have a better training error, lower training error. So that rules out, that rules out that rules out B and D, right? Or sorry, I got it right, wrong. That rules out A and C. Okay, so yeah, so you're left with B and D. So now it's a matter of understanding with the validation, right? Is your validation error for B going to be less than for A, or it's going to be greater than for A? So again, I think you can kind of graph it maybe and understand it better, right? So let's say this is model complexity. So model A is underfitting. So this is the regime of underfitting. So let's say you have A here, and then maybe model B could be overfitting, could be just right. So it could be anywhere here, right? So now let's take a look at the training error. So training error for A is here, B is here. So clearly this implies B train, yeah, is less than A train. So this is because, you see it's lower. Let's look at validation. So validation for A is going to be somewhere here. Validation for B is here. Even for this guy, it's somewhere here. So assuming B is not heavily overfitting, right? It is possible that, like, let's say your A is somewhere here. Okay. So if your A is somewhere here, your B is somewhere here, then in this case, your validation for A is lower than validation for B. But assuming B is not overfitting, B seems to be a reasonable model, and A is actually underfitting, then you'll see that the validation error for A is also higher than the validation error for B, right? So A val is greater than B val, and A train is greater than B train. So that gives you option B. Any questions on this? Okay. Right. So we spoke a little bit about overfitting and remedies for overfitting, especially in classical machine learning. So let's start with the basics, right? Increase data set size. Okay, I don't have enough data because I'm overfitting. I'm overfitting because the dimension is greater than, feature dimension is greater than sample number of examples. So feature dimension is greater than number of, so we'll call it examples, the same as number of data points. So you'll see all these are replaceable terminology, so you can replace one with the other. But examples make sense because you might have started with fewer data points, but you've done data augmentation and you've gotten many more data points. And so we'll call those examples, like the final ones that actually go into the model. So if you're in this scenario, then this implies you're overfitting, right? So since D is significantly greater than N, if I increase N, then I will be in the other side. So I'll not be overfitting as much. So that's the basic strategy, increase data set size. Well, I already have a data set. How do I increase it? So there is methods for doing that. Data augmentation is a very broad class of data-based transformations that can augment your data set. You do it. You can do synthetic data augmentation. You can do sampling, resampling. So you can sample the same data point and add it back to the data set. And then there could be other strategies as well. You can as well, if you have the bandwidth, you can even request for more data. So there are some, like in the real world, for example, let's say you had to work on a chatbot that's good at a particular skill, or it's good at a particular task. For example, if you have Alexa or Siri or maybe Portal, and then you say, hey, I want to set a timer for 20 minutes. So then the bot that corresponds to timer becomes active, and then it's able to do its job based on your ask. So I want to be good at setting timers and all the use cases for setting timers or setting alarms. And I find I'm not doing as well. So I can request more data from whom? From annotators of the data set. So you'll be working with annotators who can help you get more data for timers, right? The specific skill set that you want to do well on. So that's real data. So this is real data request. But many times it's actually expensive to annotate data and get more data. Maybe you want like thousands and thousands of data points, or hundreds, maybe tens of thousands of data points. and it's not easy to annotate them in a short period of time. It takes time and effort, and it's expensive also to annotate data. So you say, okay, let's do synthetic. So that's the second way to do data augmentation. And then you can also do resampling, like sample the same data point and add it back to your data set. So you place more emphasis on those data points. So this is one, increase data set size. And then we can do feature selection. Say, oh, actually, you know, why are we using so many features? So you can either increase n, right? So a increase n. So this is one strategy, or decrease d. This is the other strategy, or you can do both. So decrease d is what you're looking at in feature selection. You say, hey, there's too many features you're looking at. So the feature dimension is d. Maybe d is 100. Can you make d 50? So then you say, oh, well, how do I do that? Well, pick the most important features and keep it, discard the rest, and then only use those features and learn only weights for those features. And then I've done feature selection, and I have a kind of a leaner model, which will not overfit as much. Then we spoke about regularization, which the key idea of regularization is to not put too much emphasis on any of the features. Like overfitting is that, right? Okay, I place too much emphasis on gender, or I place too much emphasis on a particular attribute. And so the main idea of regularization is to clamp down the weights so that you're not emphasizing any of the features too much. So L2 is a very natural way of doing that. So you have, that's called ridge regression, where you have this penalty. So we'll call this penalty that gets added to the loss function. So this loss plus penalty is also called regularized loss. So this penalty is actually the regularization. So it's regularization because you're regularizing the weights. You're saying, hey, don't go crazy with the weights, kind of keep it, keep the weight, the magnitude of the weight in a reasonable range. So you're regularizing it by adding this penalty to the loss function. And when you actually optimize that, you're optimizing the loss, but also optimizing for keeping the weights in a reasonable range. So that's the idea of regularization, and L2 is one way to do that. And then we have L1 regularization, which is the sum of the absolute values of the entries of a vector or a matrix. And this is called lasso regression. And this is tied to feature selection, right? Because lasso not only keeps the weights down, but it also sets many of the weights to 0. So the more emphasis you place on the lasso penalty, L1 norm, the more it's going to set the unimportant features to be 0, the weights corresponding to that to be 0. So if you have 100 features to begin with, you have a low lasso penalty, maybe you end up with 90 important features. You say, well, 90 is too much. Then you increase the lambda, the weight, that the emphasis that you place on the lasso, and then suddenly you go from 190 to maybe 10. You say, okay, 10 is a good number, and maybe I'm not overfitting in that scenario. And so you get 10 most important features, but also you get the weights corresponding to those 10 features as well. So you do feature selection and learning in one shot. Okay, so that's lasso. And then someone asked last time, can you combine lasso and ridge regression? And that's what is called elastic net, L1, L2 regularization. Yeah, there's a question.
Can you do the feature the feature selection thing that you just said on for ridge regression?
Yeah, you can. You can combine it with ridge regression. So that is what is called elastic net. If you want to do it in one shot, so you can do it as a pre-processing step. Feature selection is something that you can always do as a pre-processing step. And feature selection happens, I mean, although we're talking about classical machine learning, feature selection happens all the time in the industry. Like you have these huge databases and data warehouses and data lakes, and you join a company, you're like, oh my gosh, there's so much of data, there's so many different kinds of data, and then I have to do this machine learning model where do I get started, then you might actually prune these data sets to the ones that you think are important and then ignore the rest. So you're already doing feature selection there. So that's like two-step feature selection. You select some important ones to begin with, and then you fit a model, right? Or you can do that and also combine it with more fine-grained feature selection. And there you would use something like ElasticNet, where you add the L1 and L2 penalty, and then you've already filtered things down to some reasonable. Let's say you had like 100,000 different attributes you can pick from. You say, okay, 100,000 is too much. Let's look at the ones that have a high frequency. So what's an example of this? So let's say you're working for Amazon or one of the companies that have a lot of products, right? So products can be features, right? Let's say you want to understand a customer. You say, okay, this customer has purchased, they've purchased paper towels, they've purchased batteries, they purchased hiking shoes, but then there's like 100,000 other products that they could have purchased. So, and I want to do something with this, right? I want to understand the customer. I want to make recommendations, or I want to understand the pricing or whatever. Like I want to understand fraud. There could be many different questions that you want to answer. So you have 100,000 different features or products to pick from. You might say that's too much. Let's prune it by the frequency. Which products get used more frequently? Let's start with those. The ones that are on the fringe may not actually contribute so much signal. So you would just go from 100,000 to maybe like 50,000 or something, and then or 10,000. So you're already doing feature selection at a higher level to begin with in this context, and then you start training your model. You're like, okay, I'm still overfitting. Okay, then let's apply one of these methods to fix overfitting. Does that answer your question?
So actually, so for rich regression, you're able to remove unimportant features also, like
Not by itself,
not by itself. Oh, okay.
but with ElasticNet,
Oh, okay,
you are
okay.
combining ridge regression and lasso, and you get ElasticNet.
Okay. Oh, I see, I see. Okay.
So so instead of adding one penalty, you add two penalties. So now it's a trade-off between what does this penalty do, what does that penalty do, and then I also have my loss function. The loss function is obviously trying to learn. If you leave it to by itself, it'll overfit. So then you have a lasso that says, okay, let's prune the features, and then there's ridge regression that says let's clamp down the weights. So then when you have ElasticNet, you have a combination of this. So if you applied ElasticNet and you had 100 features to begin with, maybe you'll end up with 50 features that were because lasso was involved, but also the weights corresponding to those 50 features is kind of toned down because of ridge regression.
Okay, I see, I see.
Okay. All right. So let's go a little bit more into understanding these regularizations, right? There's very beautiful, there's like some interesting geometry of these norms, right? L1, L2, there's also LP, P is between 0 and infinity. So this is in 3 dimensions. Let's look at 2D to begin with. So if P equals 2, so the set of all points in 2 dimensions says that the 2 norm is less than, let's say, 1. Okay. What is this? This is the same as W1 squared plus W2 squared is less than or equal to 1. What does this equation remind you of? You must have seen this.
The error function?
Sorry?
I mean, it's like a sum of squares, like the error function.
Yeah. Yeah. And then it's also the equation of a circle, right? If you if you equate it to 1, that's a circle. It's all the points on the circle. And if it's less than or equal to 1, it's this shaded area. So geometrically, the 2 norms squared less than or equal to 1, the Euclidean norm, right? Euclidean norm less than or equal to 1 corresponds to a circle. And in 3 dimension, that's a sphere. Okay. So this is how the geometry of a norm looks like. Let's look at this one. So if you look at p equals 1, that's the same as L1 norm less than or equal to 1. So here you have W1 in absolute value and W2 in absolute value less than or equal to 1. So this turns out to be this diamond shaped thing. So how do you know it's diamond shaped? Well, you look at the edges. So here's 1, 0, 0, 1, minus 1, 0, and then this is 0, minus 1. So the edges are when you have equality, right? So if you sum up the coordinates in absolute value on these 4 edges, you get 1, right? Like minus 1, 0, that's 1 plus 0, 0, 1, 0 plus 1, 1, 0, 1 plus 0, 0 minus 1, 0 plus 1. So you get 1. So that tells you that the edge corresponds to the diamond here. And then the inequality, which is less than 1, is the shaded area. So the L1 norm, this is called the norm ball. Norm balls. It's like if you constrain the norm to be within a certain value, the geometric shape that it takes looks like some kind of a ball. So for a Euclidean norm, that's clear. It's a ball. It's clearly a circle. So in 3 dimensions, it's actually a ball. But for L1, that corresponds to a diamond, and here you get some kind of a prism, 2 prisms, kind of 1 prism inverted. It's like the oh, sorry. This is like the if you've been to France, Louvre Museum outside, 2 prisms, reflection, right? It's exactly that. And for p equals infinity, this is interesting. We don't use it as much. It looks like a square. So p equals infinity is a little bit crazy, but the p equals infinity corresponds to a maximum of this and this less than or equal to 1. So again, let's look at the edge when, so this is one edge, this is one edge, this is one edge. Okay. So what is this? This is 1, 1. This is negative 1, 1. This is negative 1, negative 1. And 1, negative 1. So the maximum of the absolute values at the edges is equal to 1, right? So that tells you these are the edges. And then this inequality here is anything inside that. So the infinity norm ball looks like a square. In 3 dimensions, that's a cube, right? So the geometry of these norms is pretty interesting, and it also helps you understand why does L2 norm, the Euclidean norm, clamp down the weights and help you prevent overfitting? And why does the L1 norm, do sparsity, so it helps you with feature selection? So we'll look into that. But the geometry is important. So just see that the diamond corresponds to L1 and the circle or the sphere corresponds to L2. Okay, so for our discussion, we'll focus on these 2. And then you have LP with p less than 1, has a crazy shape, looks like this. So people have also used this in, I also used this when I was doing research during my PhD. But okay, so let's understand. So now that we know that these are the norm balls, that is when you constrain it within a certain value, the shape that it takes looks like a diamond or a circle. So we know that, we understand that now. Let's see how that plays with linear regression, right? So we want to see linear regression plus overfitting, or sorry, let me plus. But how does this help, right? In the context of linear regression. So assume you have this line, which you can say it's x times w equals y. Okay. Any hyperplane. So this is a linear equation, right? This is your data. This is your target, or what you want to predict. And these are your parameters or weights. Okay. So the context is clear. So obviously you may not have equality. So let's say it's approximately y. But for the sake of simplicity, let's assume it's an equality. Okay, you want to do linear regression with equality. Okay, so then you are looking at this line here. So any w that satisfies this equation has to fall on this line. Would you agree? So a w that's here or here or here or here will satisfy xw equals y. That's what this line represents. So our solution lies somewhere along this line. Okay. Now the thing is, I'm having a penalty, right? So if I look at it this way, so I want to minimize, so let's say I want to minimize the norm of W such that X times W equals Y. So there are, in overfitting, we know that there are infinitely many solutions. Yeah, we agree to this, which means that X is underdetermined matrix, or the number of rows in X is less than the number of columns in Y. So that is, you'd say D is much less than, sorry, N is much less than D. So that is X looks like this, N by D. So there's many more features than examples, right? So we're in this setting. So when you have an X that looks like this is basic linear algebra. You say X is underdetermined, this system is underdetermined. It has infinitely many solutions. Like one example we looked at last time, W transpose 1 equals 1, right? We looked at this. So this is a 1 by 2 matrix, right? Because this one data point, W1 plus W2 equals 1. So this is also underdetermined and it has infinitely many solutions. So just an example of an underdetermined system. So we're in that context. So there's infinitely many solutions. So which one are you going to pick? So then we say, well, minimize, pick the one that has a small weight, overall weight as per an L2 or an L1 norm. So then you minimize the norm of that parameter or weight vector subject to this linear system. So in terms of the geometry, and this is where the geometry, gets very interesting, is let's say you want to minimize the L2 norm, then you say, well, I'll start here because here the L2 norm is 0. Then, well, that doesn't lie on the line. So that doesn't make sense. So let's expand it. Maybe this is L2 norm equals something, let's say 0.5. Well, that doesn't still fit. So I'm going to keep expanding this ball until I hit a point on the line. At that point, I have actually minimized the weights, found a set of weights that have the least norm on this hyperplane or line. But look at where it falls in this example. It is not falling on an edge. It's not falling on any of the axes, right? But it has the least L2 norm. So the weights are kind of clamped down. If you did the same with L1 norm, then you're looking at diamonds. So I'm going to expand these diamonds until I hit the line. So that is here. And look at where it hits. It hits at on the coordinate axis. So that means the x coordinate is 0 here. So this is a simple example in 2 dimensions of how L1 norm sets some of the weights to 0 just because of the geometry of it. Right? As you expand the diamond, you're going to hit one of the axes. This is in 2 dimensions, but the analogy kind of extended to many dimensions. So let's say 100 dimensions. Why is L1 norm giving me many zeros and helping me with feature selection? It's because of this geometric property that it has. Okay. So this is one intuition behind why you would use the L1 norm or lasso. You can do the same thing. You say, well, actually x times w equals y. That's not going to happen. You can expect x times w hat be close to y, but there's going to still be some error, right? You can't expect to be 0. There's still going to be some. It's not going to fit, right? So this is the scenario where you have something like this, and then you have a line, and you say, well, I fit this line, but it's not it's not going to go through every single point. So there's going to be some error in the fit. So that's when you say, well, this is like these are the different level sets where you would kind of have this error. And for a certain error, let's say I want to find, I want to expand this, but I also want to expand this, and I meet here. So at a certain error, I'm going to meet this diamond, and I'm still going to hit on the axis. So I'm still going to get zeros in case of L1, but I'm going to have a dense weight vector when I use L2. Okay. So this is an extension of what we just did here. So this is another way of understanding it in one dimension. So let's say we're just looking at one dimension. So you have W1, that's it, there's nothing else. So this is W1 on this axis. So this is W1 square, and this is absolute value of W1. So when I try to minimize the L1 or L2 norm, what happens is the L2 norm has a high penalty when I'm far away from 0. So it's even higher than L1. But as I approach 0, the L2 norm is lower than the L1 norm. So it's not putting so much penalty on it. But L1 keeps driving it back to 0. So as you get close to 0, L2 says, well, I really don't care. There's just a small, the error is not so much. But L1 says, well, the error is still high, so I'm going to keep pushing it towards 0. So L1 has more incentive to push things to 0, while L2 is okay with keeping it close to 0 or keeping the weights smaller, but doesn't really care that it has to go to 0, because when it approaches 0, the penalty keeps going even lower and lower. So the penalty isn't high if you're not 0. But for L1, the penalty is higher if you're not 0, right? So as an example, of this. So let's say W1 is 1.5, then W1 square is 2.25, W1 is 1.5. So here, L2 has a higher penalty than L1, so L2 is going to keep pushing it down. But if you look at another example, so let's say W1 is 0.1, then W1 square is 0.01, but absolute value of W1 is 0.1. So in terms of a penalty, L2 square doesn't have much penalty for a weight that is 0.1. But L1 has a higher penalty. The penalty is 0.1. It's like 10 orders higher than L2. So L1 says, well, you're giving me a high penalty for a weight that is 0.1, so I'm going to keep pushing it down. There's more incentive for me to push it down because I want to minimize the penalty, right? So this is also another way to understand why L1 promotes sparsity, whereas L2 doesn't as much. Okay. But I like this one better. This is so much more intuitive to understand why it's producing zeros, right, as compared to L2. So this is what you would do, right? So you'd say, okay, I want to minimize x times w minus y. So this is my loss plus maybe some lambda, a regularization parameter, times L2 norm square. So this is my L2 penalty. And then I'll call this ridge regression. If I instead did this, and this is my L1 penalty, I call this lasso. So because I want to minimize, I'm trying to drive both of these down, right? And I have a trade-off. I want to drive my loss down. I also want to drive my penalty down. And because I want to drive my penalty down, this picture comes into play. Okay. So let's take a look at this in-class exercise. It's so every norm, norm is something that measures a magnitude of a vector or a matrix. It tells you how much signal is present in that vector or matrix. Also corresponds to a distance metric. And distance metric is where you compare two vectors or distance between two locations. Let's say distance between Seattle and Bellevue, right? So this in-class exercise is looking at that. And L2 norm will give you Euclidean distance, and L1 norm gives you something called Manhattan distance. So just take a look at this, and then we take a minute to answer this. Okay, so hopefully you got a chance to answer the poll. So I think just as an intuition here, so let's say there's 2 points here. Say the Seattle and Bellevue, right? So the Euclidean distance is always like, let's just go this way, right? In Manhattan, is be like, let's go this way, and this is maybe SR 520. So we know, right, this is like a triangle, and the sum of two sides of a triangle is always greater than the third side. Like that's a basic geometric fact that you might have seen. So the L1 distance is always greater than the L2 distance. Yeah, so that also helps you eliminate some of these answers. So if you're looking at the second distance is Manhattan distance, L1 distance, that has to be higher. So it cannot be 1 or 3. It has to be 2 or 4, right? So the L2 distance, it turns out, I think it's square root of 21, which is closer to 5. And so it's somewhere between 4 and 5, but it's closer to 5. So the fourth option is the right answer. Okay. Any questions on this? It's called Manhattan distance because Manhattan is a city, and you want to go from point A to point B, you have to go straight left, right, straight left, right. So it's always like left, right. And so that's what L1 also does. L1 doesn't go in like a straight line. It actually follows the streets. Okay, we'll take a look more on the impact of using L1 and L2 norms in the next assignment. Let's move on to a new topic, which is algorithmic foundations to machine learning. And so here we'll cover gradient descent, batch gradient descent, stochastic gradient descent, mini batch gradient descent. So different variations of gradient descent. And currently in the industry, mini batch gradient descent is like the mini batch SGD is like the state of the art. And obviously there are different settings within it which have been optimized over the years, but the fundamental algorithm that is used to train on large scale data, so really large scale data, is mini batch SGD. And this applies to almost every machine learning problem. So although we've only looked at linear regression so far, we're going to be covering clustering, we're going to be covering deep learning, maybe not computer vision, but natural language processing. We'll cover natural language processing. You'll see that anywhere you have a loss function and you want to optimize it, it comes down to some kind of mini batch SGD under the hood. So look at any library, scikit-learn, Keras, PyTorch, and then you look into what are they exactly doing when they're doing training. They're doing mini batch stochastic gradient descent. So if you remember the curve that we saw here, and this is training. So how do you go from here to here? That is because of SGD. So how do you make sure your loss is going down? That's because of SGD. So understanding SGD is a fundamental for machine learning. So we'll spend some time on it in this class. So this is an interesting curve, kind of looking into the mechanics of the three different versions of gradient descent: batch gradient descent, mini batch, and stochastic gradient descent. So this is currently the state of the art, but it all started with batch gradient descent. So batch gradient descent is kind of straightforward. These are called level sets, which is saying where the curve on which the function has the same value. So let's say you have a function that looks like this. Let's take a look at the other option. Okay, let's say you have a function that looks like this. If you look at the space, right? If you look at the space on which the function changes, then you'll see that the level set looks like this. So each of these curves, the function has the same value, right? So if I look at this one, right? So that's how the level set comes in, is you fix the function value, and then the space over which the function changes, the curve there depicts that the function value remains constant. So that's called the level set. So this is a plot of level sets. And here you want to minimize the level set. You want to minimize the loss. So you're starting with a high loss, right? So here I have a high loss. That means I have a higher level set. So I'm somewhere here, or I'm somewhere here, right? That's where you start somewhere. And then hopefully you hit a level set that has a lower loss value. So you're kind of progressing towards the lower loss. So that is you're kind of going down this way, right? You're decreasing the loss. So with batch gradient descent, it's straightforward. You kind of almost monotonically decrease the loss, like going down, going down. But if you look at SGD, which is this purple curve, it can actually go down and then again go up. So once this is going up, this is going down, right? So you see SGD is kind of funny. It kind of, as you work through the SGD algorithm, it can take you back, it can increase the loss, but then it'll eventually reduce the loss. So instead of seeing a nice curve like this, you might see some squiggly curve like this. This is SGD, right? This is kind of going up and down, but it will definitely kind of converge to a local optimum. So it's going to go down. So that's SGD. So people found SGD is nice because it can help scale with the data. So here's the thing with batch gradient descent versus SGD. Batch gradient descent is like works with a batch of data set, and the batch can be, the full data set that you have. The data sets that we are looking at in our assignments are something that you can work with for batch gradient descent. But once you start scaling the data set, you can't even load the batch in memory, right? So you have, let's say, 100,000 data points or a million data points. You'll go out of memory just loading the data. So it doesn't make sense to work with a batch when you can't even load the batch in memory. So that's why people said, oh, batch gradient descent doesn't work with large scale data because I have memory issues. So then you say mini batch, or let's work with 10 data points at a time or 100 data points at a time, and then I will cover the full batch in iterations, right? Maybe over. So if you have 100,000 data points and I'm covering 100 data points at a time, then over 1,000 passes, 1,000 such mini batches, I will cover the full data set. So that is the idea of mini batch gradient descent. It takes care of the memory issue, which is I simply may not be able to load 100,000 data points. So let's work with smaller batches, and then I will be able to go through the full data set. Because my learning is happening not from 100 data points. My learning is happening from the 100,000 data points. But since it's hard to load it into memory, I will work with 100 of them. But going through all of them, right, in turn, helps me learn from all the data points. So that's the idea of mini batch. Stochastic gradient descent is the extreme end of that. You say, let's learn from one data point, and then let's go to the next data point, and let's go to the next data point. So that's why if the data points conflict, you're going to keep increasing and decreasing the loss. And that's why you see the squiggly purple curve is you go up and down because you're learning from one data point. Well, one data point is not representative of the whole data set. So you might be backtracking, going forward, backtracking. But with mini batch, you still have this squiggliness, but it's not so crazy like stochastic gradient descent because you're working with many batches of data. So that's the idea of mini batch. It trades off batch gradient descent on one hand, which is nice, but it's not scalable, and stochastic gradient descent, which is completely scalable, but has a lot of uncertainty around where it's going. So people have figured out that mini batch is a nice trade-off in terms of complexity, space complexity, don't have a huge memory footprint, but also in terms of time, doesn't take it takes less training time than both batch gradient descent and stochastic gradient descent. Yeah. So that's batch, mini batch, and stochastic gradient descent at the very high level. So let's take a look at gradient descent. So what's the idea of gradient descent? So let's assume you have a function. So this is a convex function, and then this is a non-convex function, right? So this is like, let's say you have W squared. So the Euclidean norm, for instance, is convex. Even the L1 norm is convex because L1 norm looks like this, a triangle that's convex. But most functions in machine learning that you optimize look like this. They're not convex, but doesn't matter. For gradient descent, it's okay. You don't have to be convex in nature. Convex allows you to get the best optimum. Like let's say you have, let's say you start here. Is a better, say start here. So maybe I go this way, I stop here. But this is called a local optimum, right? Because locally, my loss is as low as it can be. But globally, it's not because the global optimum is here. So the loss function is the lowest here. But because I started here, I might converge to a local optimum, which is here. So with convex function, you don't have that issue Doesn't matter where you start. I start here, 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 here. I'm always converging to a global optimum because there's only global optimum for convex functions. So that's like a technical detail. But for modern machine learning, don't worry about convex functions. Non-convex is totally fine. So gradient descent allows you to find a local optimum to a loss function, which means locally you cannot do better than where you are at, right? So you like, if you look at the space in which you are, you're like, okay, I've converged to this point. All these other points will have a higher loss. So locally you're doing really well, but globally you might still, you can still do better. Turns out local optimum, good local optimum is good enough for doing good machine learning. You don't have to get to the global optimum. Any ideas why we don't have to get to the global optimum for machine learning?
It's overfitting, maybe an option.
Exactly. If I optimize for my training data set, I say this is the best possible, I have minimized the loss to the best, I have hit the global optimum. Guess what? You're globally optimum for the training data, but for your validation data, you're off. So what is the point of getting to the global optimum anyway? Because you were overfitting. So overfitting in some sense is getting to the global optimum, right? Or trying to minimize the loss as much as possible. So it's okay. You don't have to get to a global optimum for machine learning. So in the classical optimization literature, people cared about global optimum a lot. So there was a presumption that you have to minimize an objective because that's what we do. We get to the best objective. So you can even maximize an objective. It's the same thing, maximize, minimize. Let's say you want to maximize revenue, then you tell your boss, hey, we'll get to a local maximum. The boss is like, why local maximum? Let's get to the global maximum. Let's maximize the revenue, right? So typically the idea is to maximize everything or minimize everything. Don't stop halfway. But for machine learning purpose, it's okay. You don't have to optimize your loss on your training data because you might overfit. So local optimum is good enough, which works in our favor because gradient descent on non-convex functions cannot give you a global optimum. It can give you a local optimum. So that works in our favor because we don't have to overfit in that scenario. Okay, so this is a very interesting point. Is not a necessity for machine learning. Okay. Yeah. So gradient descent allows you to find a local optimum to f, which is great. So that means if I have a loss, my loss goes down this way, and I stop here. If I did global optimum, maybe I could have gone down here, right? Maybe this is global optimum. This is local, but that's okay. I'm good with local optimum as long as it's I've learned something. I'm good with that. So I stop here, right? So that's what we want to do. We want to get to a local optimum. So that's why we would do gradient descent. So let's say this is ridge regression. I can compute a gradient for this. I can do gradient descent, and then I get to a local optimum. Right? So why gradient? This is also something really, really fundamental. It turns out gradient tells you the direction of steepest ascent in a function. And negative gradient tells you the opposite, the steepest descent, right? Let's say you're standing here. Let me use a different color. Yeah, so let's say standing here. What is the direction of steepest ascent? It's this direction, right? So this would be the gradient. So the gradient has that interpretation. Actually, it's true. It's not even an interpretation. It's true that for a function, wherever you stand, you say, which is my steepest direction? Then you say, that's your gradient. Go in the direction of the gradient. It gives you the steepest direction. Conversely, if you want to go down, you just look at the negative gradient. So let's say I am standing here. I say, what is the direction in which I can go down the fastest? Then you say, go in the direction of negative gradient, which points in this direction. So because I want to minimize the loss, and I always start somewhere, and that somewhere may not be favorable, I will look to gradient to tell me which direction do I go in so that I can minimize my loss. So now here, this is one of my local optimum, right? This is also a local optimum. This might actually be the global optimum because it's even lower. But hey, I start here, I end up here. That's good enough. This is a convex function, right? So no matter where you start, the gradient is always pointing towards the global optimum. So wherever you start, you say, hey, go down this way, go down this way. So you're always, so if you're in a bowl, like imagine a bowl, no matter where you start on the surface of the bowl, you're going to hit the bottom of the bowl because that's a convex function. So the gradient is always pointing you towards the global optimum. But for non-convex, you can end up in different places. So this is why gradient is important. It gives you information on where to proceed, where to go, right? Okay, so how many people are into hiking here? Okay, see some hands going up. So think of hiking. So this is a place in Kauai, maybe it's the Napali coast or something. So let's kind of zoom in. Let's say you're standing here. Where are you standing? So you're standing here, right? Okay, that's my rough representation of you. And you want to go down to the beach, okay? So you're not going to use gradients to go down the beach, right? Because that's going to make you fall. You're probably going to go down this way. You'll go and follow the ridge, and then maybe you'll go this way, I don't know, something like this. And maybe you'll go this way. So you're going to take some zigzag path and then head to the beach, okay? Or you might actually go down this way because you say, oh, that's actually safer. I'm going to follow the ridge line that's kind of not so steep. This is the opposite of what gradient descent will do, right? So gradient descent is going to tell you, hey, why don't you go this way? Let's use a different color. So gradient descent is saying, hey, and actually negative gradient. So negative gradient is telling you, hey, why don't you go down this way, buddy? This is like the steepest direction in which you're going to descend. And obviously that's, you don't want to do that, but gradient descent will do that for you. And then you hit this point, and then here, maybe you say, go this way. And here it says, go this way. It's always picking the steepest direction. Then it says, go this way. And so it's go this way. And then maybe go this way, and then you hit the beach. So this is very interesting, right? So gradient descent is not one shot. Like I have to take a step and then decide if that's the direction that's the steepest. If you notice the pink arrows keep shifting because when I reach a new point, the steepest direction keeps changing. So I may not keep going in the same direction. So that's the whole idea of gradient descent. Take a step in the negative gradient because that's the steepest direction. It will get you, and think of this whole mountain as a loss function. So that's the other thing, is this whole mountain is a loss function, right? The loss here is the maximum loss. You're looking at the maximum loss, and this is like the minimum loss. So you're going from maximum loss to minimum loss. So you start at some point. This is not a point of maximum loss where you're standing. That's still high loss, but it's not maximum loss. And you want to keep reducing the loss. So you take a step in the negative gradient direction. You make progress. Then you reevaluate which is the direction now that I should proceed in, and that might be a different direction. You go in that direction, take a step, keep going, and then.
Professor, I have a question.
Yeah.
Does it matter the size of step you take? Like
It does matter. It does matter. For instance, let's say you're standing here. So you're standing here, and then gradient tells you go in this direction, right? Sorry, maybe go in this direction. So you keep. So it's saying go this way. So you're going to trace this curve, and then you come here. If I keep going left, I will go up. Does it make sense? So I shouldn't keep going in the same direction. I shouldn't take a big step, because if I take a huge step, I'll end up here. If I take tiny steps, I'm going to go here, 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 and then here. I probably need to go this way, and I go this way. So it does matter, right? If you take a huge step, you will end up in the opposite of where you want to go. So I want to be cautious, but if I take a too small step, I'm going really, really slow. I'm going to take forever to make progress. So there is something called the ideal step size, where you make progress, but you're not overstepping that you actually end up in the other side, in the wrong direction, right? Or a wrong place. So that's the idea of gradient descent, is take cautious steps and reevaluate, and then keep going towards the minimum. Okay. So this brings us to the algorithm for batch gradient descent. So let's say we want to minimize a loss function, so we'll call it L. For instance, for linear regression, this is L of W equals XW minus Y. So you see, this is the distance between XW and Y. So the Euclidean distance that we just discussed, right? So that's the loss function. And maybe you normalize it by N, so by the number of data points. There's the average distance between any given point, and it's between the target value and the prediction for any given point. That's the average loss. Say I want to minimize this and find the best parameter that does the job. So I start with some point. I randomly initialize. This is the same as saying pick some point on the mountain. I don't know where, but pick some point. Maybe I start here, you start here, maybe I start here. So that's like a starting point. So that's like random. So randomly initialize where you want to start. You can use some random function to do the initialization, and then you take a step in the negative gradient. Take a step in the direction of negative gradient. So this step is called learning rate. So learning rate is the step that you would take. You may not want to, like we said, we want to be cautious with the steps. If you overstep, then you might actually increase the loss. So being cautious. So the learning rate is, and there are things called learning rate schedulers that you can find. Let's say using PyTorch or one of these machine learning libraries, they will have learning rate schedulers, and you set the learning rate scheduler. It'll schedule how the learning rate should change as you proceed through the algorithm and as you're taking the steps. Okay, so the learning rate tells you how cautious you want to be in taking a step, and then reevaluate. So you get to a new point, and then you compute the gradient there, and then reevaluate what step you're going to take. So you're cautiously going through and then making progress. So that's the idea of gradient descent. And then you iterate through step 2. So you keep repeating step 2 again and again. Right? You loop through step 2 until you converge. That is, you're not making any progress anymore. Okay. So okay, here I kind of flattened out. So here I kind of stop because I'm not making much progress. Okay, so this is the whole idea of gradient descent. And there are, if you go into the fine details, there's like different ways of picking learning rates and different ways to ensure you're making progress. So people have published papers on this, and there's a lot of details in there as well. So we'll maybe spend time on learning rates when we get to deep learning, where we have different kinds of rules for learning rates. But for now, assume there's like ways to pick it. Okay, so that's batch gradient descent. So batch because you're computing the gradient with respect to W, and you're using all the data points. The loss function is averaging the error across all data points. So that's the batch. So that's why it's called batch gradient descent. Okay, actually, maybe I always feel like, okay, let's come back. It started. Okay, so gradient descent in one dimension. This is like really, a starting point to understand this, right? So let's say I'm here. This is my W0. So W0 means the starting, say, starting weights. So I initialized it at random. I'm here. So this is one dimension. So I can only move this way or this way. So the gradient is going to point to the left or the right direction. It's very simple. So I decided to take a step, and I go here, W1, and I go here, W2, W3, W4, W5, W6. Now imagine I take a huge step. Okay, let's think of it this way. Let's say I'm at W2 and I decide to go take a step that's this long. So from here, which is W2, I end up here, which is W3, and look at the loss corresponding to W3. Right, it's here. So that means I go from here to here. This is a pitfall of a large step size. And then here, when I reach here, the negative gradient is going to point this way, right? If I continue with this large step size, I will go from here this way, and I might end up here, which is W4. So I'm kind of zigzagging in this fashion. So I'm going this way. So I'm actually increasing the loss with large step size. So this is the pitfall of having too large a step size we see in one dimension. Instead, if you go in this learning rate seems to be good because I take a step and I evaluate what's the direction of negative gradient. It's always this way, this way, this way, this way. So I take small step size and I reach the local optimum in this case. If I take, so sometimes people do gradient descent, like you might implement it yourself, or you change the step size. You're like, okay, let me just set a large step size. I'll converge faster, and you suddenly realize you're getting really crazy weights, and everything's going out of hand. That's because of this phenomenon. You've taken really large steps that you're actually blowing up the loss instead of reducing the loss. And the same holds true for loss function 2 dimensions. So want to be cautious with the step size. Yeah, maybe we can do this as an exercise. Speaking of gradients, we'll have more of this in the conceptual assignment too. Is so like we spoke about, did we do this last time? So let's compute the gradient of the regularization function or regularizer here. So remember, gradient is a vector of partial derivatives. So that's the definition of gradient, right? So here you would basically be computing the partial of this, partial of this, and so on. Partial over WD of R of W. And you put this all into a vector, right? So you get a long vector, and that's your gradient. So you represent it this way: inverted triangle, gradient with respect to W of the function that you care about. So here, what I would suggest is expand this out. So when you expand it, you get W1 squared plus W2 squared, WD squared. So compute each of these partials and then put them into a vector and then see which of these correspond to that gradient. Okay. So we'll pull out some pen and paper to do this. Let's take like a minute or two to look at this. So what is the first partial? Let's look at that. What is this? If someone wants to call it out.
2 lambda W?
Yep.
Or okay.
2 lambda W1, right? Because you're taking the partial with respect to W1. And the same holds true for anything. Like say Wj, it's 2 lambda Wj. So this tells us that you can pull the 2 lambda out and you get W1, W2, WD, right? So it's 2 lambda times this vector, and this is just W, because W is the vector of the elements W1, W2, W3. So a little bit confusing. If you think of W as a scalar, W is actually a vector, and W1 is a scalar, W2 is a scalar, WD is a scalar. And when you put together W1 through WD, you get the vector W. So sometimes in textbooks, you might see a W that's bolded. So it's bold. So if it's bold, it's a vector. If it's not bold, it's a scalar. That's a little bit of extra notation to make it easy to understand. But always ask yourself, is this a vector? Is this a scalar? Then it becomes easy for you to understand. So you just put it together, you get 2 lambda W. So it's the same way. I mean, computing the gradient of linear regression loss function, a little bit more involved because it has matrices in there. But you can do something similar. Take the partials, start with the partials, and then put it together and see how it comes together and what does that give you, right? So that's how you would do gradient computations. With most of the libraries that we have, that do machine learning, the differentiation is usually automatic. So they use different rules for derivatives, chain rules, and things like that. You just have to specify the loss functions. It understands any given loss, any given simple function, what's the derivative look like, and then you have combination of these simple functions. It knows how to chain. It knows how to chain these derivatives and gives you the final gradient. So the differentiation is all automatic once you specify the loss function. But good to know that this is how you compute the gradient, right? And this is what's happening behind the hood. Okay. Wait, aren't these the same? Oh, this is the same. Okay. Yeah. In the next assignment, conceptual, we'll look at more on this. So some properties of gradient descent. Gradient descent converges to a local minimum. We spoke about this. If it's a convex function, all local minima become global minima. There's no local minima. It's all global. So wherever we start, gradient descent usually finds a local minimum close to the start. So this is like, what we spoke about. If you have a function like this and you start here, you're going to end up here. But if you start here, or let's say you start here, I might end up here. So depending on where you start, you end up at an appropriate local minimum. And then we spoke about the effect of learning rates. Small learning rates, you're going to have descent. Big learning rates, you might actually explode the loss function. And we spoke about this in the beginning as well. The behavior of gradient descent for batch, mini batch, and stochastic have this kind of a flavor. Let's look at stochastic gradient descent. So this is one of the fundamentals. So what's the idea of stochastic gradient descent? The loss function is actually a sum of loss functions over data points, right? So let's say n was 100, your loss function would be something like 1 over 100 times L1 of W plus L2 of W, so on, L100 of W. So you're looking at the loss across every single data point and averaging it, which makes sense. I want to minimize the average loss that I'm incurring across different data points. So the idea of stochastic gradient descent is pick any one of them, pick L2 or pick L7 or pick L8. So that is, I am looking at the loss for a single data point and trying to minimize that, right? In other words, you're also gaining information only from one data point at a time and updating your weights. And what you gain from one data point might contradict what you gain from some other data point. So that's why there is this zigzag behavior. So initialization is the same. Initialize your parameters. So let's say you have 100 dimensions to the data, to the parameters. You initialize it at random. And then you pick an index I between 1 and n. So there's n data points. So pick some index. Maybe I is 20. So yeah, I'm picking the 20th data point and seeing what can I learn from the 20th data point. So I'm learning from all data points, right? But in stochastic gradient descent, you learn one data point at a time. So I pick the ith data point. I take the gradient with respect to that. So I'm saying, hey, the loss function can be reduced by using the data from the ith data point and optimizing, right? So taking a step in the negative gradient direction. But that's only for the ith data point, right? I'm not using other data points. And I take a step and then I repeat, right? So I repeat steps. Oh, I think this has to be part of this. Yeah, I'm sorry. This is probably step. This is 2, this is 3, and this is 4. So repeat 2 and 3 until W converges. So pick a data point at random, see what can you learn from that data point, move on to the next data point, You might pick, so typically what people do is they kind of permute the data points. So you can just permute it beforehand. So let's say I have 1, 2, 3, 4, 5, 6. There's 6 data points. I permute it. I might get something like 5, 6, 2, 4, 1, 3. So I go through data points in this order, but this is a random permutation. So that's the stochastic part, right? So the S in SGD has to do with this random permutation. Randomize the order in which you go through the data points And the randomization is key to SGD because that's how it works. You're not biasing towards any one order. And if you didn't do randomization, you permuted it in some specific fashion, it will not work the same way as SGD does. So the randomization is very important, is the key. So you're not only randomizing the starting point, which you do anyway for any algorithm, but you're also randomizing the order in which you pass through the data points. And then you'll keep learning from different data points until you converge. And it has been shown that SGD converges. So you might say, well, if you're learning from different data points, maybe there is some contradiction, there's some zigzag, you might actually not converge, but people have shown that you will converge. So that's the theory behind stochastic gradient descent that shows that you will always go to a local optimum if you choose a step size right. So stochastic gradient descent works, right? So we know that it's just going to take it's going to be like zigzag, and then there's going to be a lot of zigzag, but you will eventually go down and you'll probably converge there. So, and this solves the memory issue that batch gradient descent has. Why? I have 100,000 data points and I can't load it. So I only load one data point at a time. That's super easy. I can load a single data point without any issue, right? And then I learn whatever I have to learn from it and I move on to the next data point. And I may not just do this once, I might do it multiple times. So that's called passes. So pass goes going through the data set once. So I might have k passes. So that means k times go through this random permutation and then you're done. So for really large data sets, you may not even worry about this rule here. You might just say, let's do 3 passes through this data set, and then hopefully I'm in a good place. And in practice, that kind of a thumb rule does work. So do 3 passes or 4 passes through a data set in the stochastic fashion of picking one data point at a time and making this progress until you get to a local optimum. Okay. So as we saw here, this is the SGD behavior in the level set space. This is going to be a zigzag behavior going up and down, but eventually converging to a local optimum. In practice, we do mini batch SGD. So what's the idea? So you have B batches, and let's say K is the batch size. Maybe K is like, let's say 150. So you look at 150 data points at a time instead of looking at one data point. And then learn from 150 data points in one shot, and then go to the next 150 until you've done one pass. And then you do a few more passes. So the idea of passing through the data set a few times is the same, but how you pass through the data set is different because you're looking at a mini batch instead of a single data point. So it's an extension of SGD. So randomize. This is step 1. Maybe this is step 2. Pick a batch of k data points at random between 1 and n. So maybe I1, I2, I3, Ik. And then do gradient descent. So here you see I'm learning from k data points, right? In SGD, learn from one data point. So you're learning from k data points. So the gradient is also averaging, or it's summing or averaging from k data point. So the gradient is informed also from the k data points instead of being informed by one data point. So you have a better sense for where to go with k data points as compared to one data point. And you still have a learning rate because you don't want to overstep and increase the loss function. And then you repeat, so this is 2, this is 3, this is 4. So repeat steps 2 and 3 until you converge. So that's the same. So batch gradient descent versus mini batch. Batch gradient descent is like a smooth profile until you're done. With mini batch, there is still a zigzagging behavior, but not as crazy as stochastic gradient descent. The zigzag still comes because you're looking at, let's say, 150 data points instead of the entire data set. So what you learn from 150 data points may not fully reflect what you will learn from the full data set. So there's going to be some mismatch, and so the loss might go up a bit, but then eventually it keeps going down. Okay, this is a table that kind of summarizes the different, mainly gradient descent, mini batch. I mean, we don't look at SGD anymore, so it's mini batch or gradient descent. So for the data, you use all of the data in gradient descent. You only use mini batch here, right? In terms of randomness, it's gradient descent is deterministic, except for the starting point. So you can also put a random seed for a starting point, and then that fixes the starting point. Let's say you were to do gradient descent for your linear regression problem. Okay, if you use a random seed, then you will always start with the same random starting point, right? So otherwise, what happens is you run it the first time, you get some result. You run it the second time, you get a different result, and you're like, wow, I didn't change anything in the algorithm. Why am I getting a different result? That's because your random starting point changed. So if you fix the seed, you'll get the same result. Okay, so that's why we say it's deterministic. If you fix the seed, it's deterministic. But mini batch is stochastic because the way you pick the mini batches is random, right? So if I have, this is my n data points, I divide it up. So this might be my first batch. This might be my first batch. This might be my second. This might be my third, fourth, fifth, sixth, seventh. So this is this is like, each of these is a mini batch. So here, yeah. So the way I am picking these mini batches, the order in which I'm going through it is stochastic. So that's randomness is stochastic here. And the error reduction is monotonic in gradient descent. So you're constantly reducing the loss function. So also loss, but with mini batch, it's stochastic. There's a zigzag behavior. Computation can be high with gradient descent because you're using all of the data points. So imagine you're dealing with 100,000 data points. Okay, I have a very powerful machine with a lot of memory. I am able to load everything, but I still have to do computation across 100,000 data points. So the computation is still high. So we say the per iteration complexity is high. The per iteration complexity for mini batch is low because you're only dealing with 100 data points or 200 data points. So memory for gradient descent is usually intractable because for large data sets, I can't scale. But even if you're dealing with a billion data points, like some of the new modern machine learning methods, let's say GPT-3 or Chat GPT or any of these BERT models, they use millions or even billions of data points. Cannot load it to memory, but still can do gradient descent because I'm only loading some of it, a small fraction of it at a time. So it's tractable. Convergence, okay, this is, you usually use relative error to decide convergence for gradient descent. For mini batch, you just say, let's do a few passes on the data sets like we discussed. Local minima traps, yeah, gradient descent is prone to local minima issues. Here's a little bit of a finer point. Someone, there's papers on this that show that yes, both gradient descent and mini batch stochastic gradient descent converge to a local minima, but mini batch, because of the stochasticity, is able to get a better local minima than gradient descent. So there is an advantage to using mini batch, other than just the memory improvements that we expect. There's also better local minima that helps you get a better validation error. So that's called generalization. So generalization is, if you can train on trained data and do well on unseen data, you are able to generalize well. So mini batch stochastic gradient descent generalizes better than just gradient descent. But there's papers that are that have been published that show that as well. So let me write that down. Okay. Oh, wow. Okay. All right. So any questions so far on, there's a lot of material and we've gone through a lot of things very quickly, but any questions on gradient descent, stochastic gradient descent, the idea of doing gradient descent, scalability, loss functions? Yeah, just think of it as like, I think the analogy of hiking or going down a slope is really good for gradient descent, right? So a lot of it is intuitive, but if you go into the details, there's also a lot of details, the like technical details on understanding learning rates and convergence proofs and things like that. So we don't go into those things in this class, but we do cover all the intuition, right? The intuition behind this, intuition behind that. So we'll stay at that level. But this is kind of a fundamental, so really fundamental thing to machine learning. So we've covered it. I mean, we've gone through it, and you'll get to work on this in the conceptual assignment as well. Okay. The next topic is spam classification. So we'll go into it. So we'll be going into classification. So we're moving from linear regression to classification. So we'll start on that in the next lecture. And I think your next assignment is also on spam classification. There'll be a Kaggle contest. So you can work in teams of two, or I have to discuss it with Ayush. We'll do teams of two or just yourself. But you can make submissions to Kaggle and see where you stand with respect to your peers. Yeah, it should be fun. Okay, so I'll stop here. And if you have any questions or thoughts, you can feel free to stay back, or we'll see you again on Tuesday.